Okay. Right. This morning we're going to talk a bit more about hot water boilers and some controls. The controls systems that I'll talk about this morning are, I've just taken them out of the ERA guide, which I'll mention further down. There's a number of ways you can control boilers, and probably the best way to go about it is to talk to the controls companies, get their ideas, and the boiler suppliers, they will have their requirements as well, and make sure that all those requirements are incorporated. I mean, you can come up with your own ideas, but just be sure that the boiler suppliers are happy with them and they're achievable with the controls going into the project. Okay, so has everyone got the notes up there? If you can see the notes. All right, good. So in stage 2 of the training program, we looked briefly at HVAC systems utilising hot water boilers as the source of heating for air conditioning or process temperature control. In this session, we're going to look a bit more closely at the boilers and typical control systems. The energy source for hot water boilers, they're not really boilers, they're not boiling the water to 100 degrees, they're heating it up to, say, 80 degrees for the heating system, but they're commonly called boilers. They're not steam boilers, they're hot water boilers. The energy source is normally natural gas or LP gas, but could be oil if there's no gas available, such as diesel. The two most common boiler types are the conventional or non-condensing type and condensing boilers. The temperature range of a conventional or non-condensing hot water boiler is typically between 80 degrees leaving the boiler and going out to the field, and 60 degrees entering the boiler and coming back from the field. Return water temperature at 60 degrees is necessary to prevent condensation of vapour in the flue gas, and hence that prevents corrosion in the boiler and flue. This is not uncommon when you get water temperatures below, we're going to talk a bit more about this shortly, but below 54 degrees, you start to get condensation of the vapour in the flue gas, and that can cause corrosion in the boiler and the flue. And I know that previously I've had a conversation with Anand about that. He struck a boiler that had rust in it. That's probably the cause. It's quite common. The temperature range of a condensing hot water system is typically lower than a conventional system because the flue gas vapour condensing process occurs at hot water return temperatures up to 54, so less than 54 degrees, the condensation will be occurring. Above 54, the condensation stops. That's the magic temperature. So that's one to just put in your memory banks or make a note. If you're looking at condensing water boilers, below 54 degrees return temperature is necessary. Hot water boilers are typically either water tube or fire tube. That means that either the water's passing through the tubes in the boiler, or the fire is going through the tubes. I think it's probably more common that we have water tube boilers where the water is in the tubes. And the heat produced to heat the water is usually by one or more gas burners, which can be either a forced draft or gun type or atmospheric burner. The hot water flow rate through the boiler is normally constant for a conventional boiler and variable for a condensing boiler. So I'll just show you a couple of pictures that we've had up before. This is a dirty old conventional boiler, obviously not in action at the moment, but has that come through okay? Can you see that picture? Good. This is a gun burner here. The gas is burnt in there and the fire goes into the body or the vessel, and the water is passing through the tube. So the water connections are shown here, and the flue connection at the back there. So the fire, the heat passes through the boiler and then up through the flue at the back. This is a smallish condensing boiler, much more complicated than a conventional boiler, but much more energy efficient. And we'll talk a bit more about that shortly. Condensing boilers have an additional heat exchanger for recovering heat from the flue gases. This improves the energy efficiency of the boiler. The improved energy efficiency is achieved because water vapour in the flue gas is condensed by heat exchange with the return hot water from the field, and the energy extracted in the process preheats the return water entering the boiler. The water then passes through the main heating chamber, where it is further heated to the design temperature for the project and supplied back into the hot water system. So I'll show you a schematic of the condenser water boiler, a simplified schematic, which is quite helpful to understand how it works. So the blue line here is the so-called cool water. It's still hot water, but it's been cooled by heat exchange out in the field with the fan cool units and air handling units. This says radiators. We don't do that often, but sometimes we do. But inside the boiler, there's a heat exchanger in the flue gas. So over here is the gas coming in through the burner, and this coil is where the water is passing through and getting heated. So this is what you'd call a water tube boiler. The water is in the tubes, the fire is outside the tubes. So the hot gases heat up the hot water, and then it goes through another heat exchanger where this condensation process occurs. Because if this water is below 54 degrees, the water vapour in the flue gas will be condensed. That's just a fact of nature. That's how it works at that temperature. And the latent heat from that's extracted from the flue gas preheats the hot water coming in. So you pick up energy efficiency by preheating the hot water coming in. And as it passes through the boiler and comes in direct contact with the heat from the burner, it heats up more and then leaves the boiler at the design temperature. Well, just while we're on that, the next comment here is that the condensate or condensed water from the flue gas is corrosive, so it's acidic. So the flue heat exchanger is made from a corrosion-resistant material such as stainless steel. Some manufacturers use a high-grade aluminium. Just be careful if you're selecting them that you are confident or that they can assure you that the material for the heat exchanger is going to be resistant to the acid in the condensate. The condensate, you need a neutralizer to neutralise the acid when it's leaving the boiler to avoid damage to piping systems, sewage systems and treatment plant. So just going back to that schematic again, the condensate, which is acidic, drops into the drain of the boiler. It doesn't show it here, but I've added a note that you need a neutralizer in the drain. Now you'll find when you're talking to suppliers for condensing boilers that they will always offer a neutralizer. You don't have to take it, but it's a good idea to take it. We've got another couple of people joined us, Stephen and Siobhan. Welcome.
Thank you.
Good to see you here. Okay, so we'll continue on. Some condensing boilers have multiple burners, which enables efficient operation of part loads. Condensing boilers can generally operate at reduced water flow rates, which also provides savings in pump power. So the conventional boilers tend to have a fixed flow rate of 100%. Again, look, you can check with the manufacturers. there may be options available for reduced flow rates on conventional boilers, but normally it's 100% flow. Condensing boilers can go down to very low flow rates, which is a big saving on pump power and allows you to just provide the amount of water that's needed for the heating in the field. So through all these heat recovery process, the lower flow rates, condensing boilers have greater energy efficiency than a conventional boiler. The improvement in energy efficiency may be as high as 15%, provided they're carefully selected, monitored, controlled, and maintained. Unfortunately, you don't get something for nothing. A condensing boiler costs 30 to 50% more than a conventional boiler. So if you've got budget constraints on your project, a conventional boiler is probably going to be the way you go. But if you're looking longer term, and it's more common these days to use conventional condensing boilers to pick up the energy efficiency that comes with it, and the environmental benefits with that. It's important to understand the factors that optimise their operation and in order to obtain peak efficiency and energy cost savings. So it's talk to the suppliers. There's plenty of literature available on the internet with all these things I'm talking about. You can Google what I'm saying. You'll find heaps of information. So it's all out there these days. It's not like 20 years ago when you had to go searching books and things. It's all readily available now. When you're looking at the type of boiler to use on a project, so you need to consider the following factors. Energy efficiency requirements. The NCC has requirements for boiler efficiency as well. So you need to comply with that. The cost, capital cost, and obviously the running costs. Temperature range suitable for the project, and always remember that condensing boilers, they're going to operate at a lower temperature because you have to have a return temperature less than 54. You can search online and you'll find that the efficiency just continues to improve as the return water temperature gets lower. But if you've got a lower return, as the return water temperature goes down, obviously the supply temperature is coming down as well, and that might affect your heating coils, your heating efficiency out in the field. So there's a few factors to consider, but condensing boilers certainly going to give you a greater efficiency. Return on investment, over the longer term, the savings in energy cost may be enough to recover the initial capital cost. And that's the whole idea, that over time, you're going to recoup that initial investment in a condensing boiler. This comment highlighted here is really for the benefit of the MEPAC people. We have internal checklists, engineering checklists and boiler checklists when selecting or reviewing the selections. Okay, now we'll talk about alternative sources of heating hot water. As you're all aware, gas is being phased out gradually. Whether it gets completely phased out, we'll have to wait and see, but the cost is going up. The cost of electricity is going up as well, but they're finding alternative sustainable sources of electricity now. So electricity seems to be the way to go in the future. There are several alternative methods of generating hot water using electricity instead of gas or oil. There are many types and sizes of electric heat pumps available for heating water. These machines are basically refrigeration machines which reject heat into the hot water circuit for use in spatial process heating. There are also heat pump chillers and four-pipe chillers available, which can provide both chilled and heating water. So we talked about these in the last session, which was 6 or 7 weeks ago. So you can get a chiller that can operate in cooling or heating. So a heat pump chiller can provide chilled water or heating water, but not at the same time. But a 4-pipe chiller can provide chilled water and heating water simultaneously. So they're worth considering. I've got a few pictures of those, but again, you can search all this stuff online and have a look for yourself. So this is a Carrier brochure. There's a water-cooled screw heat pump. So that's a chiller and a heating machine. A range of 270 to 3,700 kilowatts cooling and up to 4,000 kilowatts heating. It's another one here, smaller one. This is still a scroll chiller, air to water heat pump. So you can get water cooled or air cooled chillers, heat pumps. And I've just got a picture of I don't know whether you've had much experience with 4-pipe chillers yet, but this is one particular type, Blue Box. If you Google Blue Box multifunctional chiller, you'll find this, and there are lots of others. Interestingly, most of the multifunction chillers come out of northern Italy. That's where they're made. That's where the technology seems to be developing. So there's quite a few manufacturers who make the multifunction chillers, and they're a 4-pipe chiller, so you can have cooling and heating simultaneously. So very energy efficient, but they have a few technical requirements. As long as you comply with those requirements, for instance, on both the cooling circuit and the heating circuit, they require buffer tanks. So just things like that. You need to read their data, what their conditions are, and they can be quite useful. But they go up to, according to this, up to 944 kilowatts. So they're not huge, but they can be quite useful. And I think Woolworths, if you've done a Woolworths job recently, I think they are actually specifying multifunction chillers in their requirements, in their design brief. So be aware of that. So when determining the best choice of heating source, consider the following items. Sustainability and future proofing. As I said, gas may not be available in the future. Keep yourself abreast of those developments and select the heating source that's going to be good for the life of the project. Heating load requirements, energy availability, space constraints. Some of the, if it's an air-cooled heat pump, you've got environmental considerations, corrosion. It's going to be out in the weather, compared with a water-cooled option, which may be protected in a plant room. Energy efficiency requirements, cost, temperature range suitable for the project, and again, return on investment, energy savings versus initial cost. Okay. Now we'll move on to some control requirements. All boilers, such as well as with chillers, have a specified minimum water flow to ensure safe and stable operation. In some cases, the minimum flow may be the same as the design flow. So you'll probably find most conventional boilers, the flow is the flow. There's no minimum, or the minimum is 100% flow. In general, particularly with condensing boilers, the minimum flow will be less than the design flow. So when you're designing a heating water system, it's necessary to ensure that the water flow in the system doesn't drop below the required minimum flow through the boiler. So you need to look at the technical data for the boiler you're considering, or speak to the suppliers, manufacturers, and find that out, because there will be a minimum flow requirement. If you go below the minimum flow, you can sort of guess what's going to happen, that you haven't got enough water flowing through the boiler. You've got, I'll qualify this, you do have a control system which is going to control this, and you have safety devices on the boiler. But if you've got a very low flow, below the minimum required, there's a chance that you're going to boil the water. And if you boil the water, that's going to be a catastrophe, because it's not designed for boiling water. Okay? The pressures go too high, temperatures are too high, and things are going to fail. So the minimum water flow will vary for different boiler types and manufacturers, and you need to find out what that is. So check it out in the tech data. The flow through the heating coils in the field is controlled by either two-way or three-way motorized control valves. So these are the valves in the pipework at the air handling units or fan coil units. Two-way control valves generally provide better energy efficiency, as the flow through the coil will be reduced as the load reduces. So they just close down when the load's reducing. But when the flow reduces, the system pressure will go up. Okay? So in order to control the increase in system pressure and flow reduction, we need a two-way bypass valve. Well, the two-way bypass valve is normally installed between the flow and return pipes to modulate towards open to maintain at least the minimum allowable flow through the boiler. So I've done a little sketch here. Excuse the quality of the sketch. This was just a quick one I did up. So here's the boiler on the pump. And the water goes through the boiler and out to the field to the air handling units, which all have control valves, typically two-way control valves. So as those valves start to close, if the load's reducing in the field, the pressure between the flow and return pipes is going to increase. So you've got a differential pressure sensor here, which senses that change in pressure and starts to open the bypass valve so that water will bypass the field and go back through the pump to the boiler and maintain the required minimum flow through the boiler. The same sort of thing happens with chill water systems, and we talked about that in our last session with chill water. There's a differential pressure sensor shown here across the boiler. It's actually quite often across the pump, and really that's just an indicator of flow. So if there's a pressure differential across the boiler or across the pump, it's indicating that there's flow, and we'll talk about that a bit more later on, because that's an important feedback to the control system to say that there is flow in the system, and therefore the boiler can start. The boiler safeties won't allow it to start if there's no flow, because that's, like I said before, that's a bad situation. It's going to get too hot in there. As I said, the bypass valve responds to a differential pressure sensor or transducer installed between the flow and return pipes downstream of the pumps. The actual location of the bypass valve is determined to suit the system design, but normally they're in the boiler plant area, in the plant room, so they're accessible and can be set up. Now, sizing of the bypass valve. If you look at a simple heating water system with one boiler only, which operates on design flow at all times, when the field is at full load condition, the flow to the field will be 100% design flow. As the load in the field starts to reduce, the control valves will start to close and reduce the field flow, thereby increasing the pressure in the system. As the pressure increases, the differential pressure will open the bypass valve to maintain the flow through the boiler. So I've just repeated myself, but just to rub that in a bit. So when you're sizing the bypass valve, an assessment must be made of the maximum flow through the bypass and the corresponding pressure drop of the bypass valve. So we need to work out what is the flow through the bypass for the maximum. And the valve pressure drop, bypass valve pressure drop at maximum flow should equal, as closely as you can, the field pressure drop at design flow to maintain the system stability and efficiency. And the bypass valve needs to be handled the entire flow range of the system. So just going back to this little sketch, the bypass valve needs to have a similar pressure drop to the field. So from where the bypass is connected to the flow and return pipes out to the field, downstream of there to the field, and from the field up to those connection points, the pressure drop that's calculated for the field needs to be the pressure drop you use for the bypass valve when selecting it. Okay, so that's important, and it's often a tricky thing to work out, but if you just work on that basic fundamental, you should be okay with selecting it. Now, some systems are going to be different, but in general, that's how it's done. Normally, the bypass valve will be sized for 100% design flow at the calculated field pressure drop on the field side of the bypass valve. So based on that, it's normal for the bypass valve size to be smaller than the corresponding pipe size, as the pressure drop through the bypass valve will be relatively high. So I hope that makes sense. It's relatively simple. It's a little bit hard to get your head around sometimes, but once you've calculated the field pressure drop, excuse me, you can use that for sizing the bypass valve. The bypass valve will be small. So let's say you've got a pipe size of 100 millimeters going out to the field and a flow rate of 10 litres a second is your design. Then the bypass valve will have to be capable of handling 10 litres a second, but at the same pressure drop as what the field is handling. So you might have a pressure drop of, say, 200 kPa in the field. So the pressure drop through the bypass valve will have to be 200 kPa, and therefore your bypass valve might be only a 50 millimeter valve. So it might look a bit funny, but it'll be correct. It won't be the line size, because if it is, it won't work properly. It's got to be small to provide a restriction so it can control. If all of the field control valves have closed, the flow through the bypass will go to 100% design flow, and which indicates there's no flow in the field, no load in the field. At this point, the boiler is not required and will shut down. It'll shut down under its own controls. In that little sketch I showed, there's not much there in terms of the controls. The boilers have a lot of their own onboard controls, and there'll be other controls in the field, such as maybe a flow meter, temperature sensors. All these things act together to pick up that the load in the field is gone, and the boiler will shut down. Now, I want to talk about hydraulic separators. Some of you may have come across these. In recent years, I suppose the last 10 years or possibly a bit more, it's been common practice to install hydraulic separators downstream of the boilers. Some of you weren't at the chilled water talk, but we talked about decouplers in the chilled water system. For a primary-secondary system, there's a decoupler between the primary and secondary system. Well, a hydraulic separator is a similar device. It's less. It's just a simple decoupler, I guess you could say. It separates the boiler loop, which is the primary circuit, from the field loop, which is the secondary circuit. This creates a simplified primary-secondary system similar to a chilled water system, but uses a hydraulic separator instead of a decoupler. So I'll just show you a diagram of a hydraulic separator. It It looks like this. Again, you can Google this. You can Google hydraulic separator, and this will come up, and you can have a read through all this, and I'll briefly go through it. But basically, you've got 4 connections. You've got 2 for the primary side from the boiler to the boiler, and 2 for the secondary side. So 1 to the system and 1 back from the system. And this is basically a tank, a bit of pipe with some nozzles on it or flanges. But it also provides, it functions as an air and dirt separator as well. So it lets the air out automatically. And it's also got a drain valve, so you can drain any dirt that collects in the bottom of this little tank. Primary loop has a dedicated primary pump for each boiler, which circulates water through the boiler and the hydraulic separator back to the boiler. The secondary loop has dedicated secondary pumps, which circulate water through the field loads and back through the hydraulic separator. So let's have a look at a primary secondary system. I've just changed this from the chilled water system. It's pretty much the same. So you've got boilers in the primary loop. They go down. The hydraulic, this is like a decoupler, hydraulic separator in this case. So the water from the primary loop can circulate through there, back to the boilers. The secondary loop, which has got the air handling units, fan cool units and so on, has its own set of pumps. Goes out through the air handling units, back to the boiler, but can now also circulate back through the hydraulic separator. So I'll talk some more about that. The hydraulic separator not only separates the 2 circuits, but also serves as an air and dirt separator, which I mentioned before. There are 3 possible flow paths within the hydraulic separator. Firstly, if the primary flow is equal to the secondary flow, or a balanced flow, the primary water passes straight through the hydraulic separator to the field with minimal mixing of circuits. So if we go back to the hydraulic separator, flow path number 1, we've got a balanced situation where the flow in the field is equal to the flow being produced at the boiler. And that's not necessarily a common situation, but it can happen. That it's 100% load in the field, all the valves are open, so all the water from the boiler is going straight to the field and back again. So in this case, the water basically flows straight through the hydraulic separator and straight back from the secondary side. Secondly, the flow in the secondary circuit is greater than the primary circuit because the field flow requirement is greater than the boiler output. Okay, so the field is requiring more water, more hot water, but the boiler capacity at that time is not able to provide enough water. So in this case, a portion of the water in the secondary circuit will mix with the primary water in the separator and recirculate to the field without returning to the boiler. This will obviously decrease the temperature of the supply water in the secondary field circuit. Now the boiler controls and the system controls are going to compensate for this, but so what's happening? Number 2, water's coming from the boiler, and it's going out to the system, but the system requires more water than the boiler is actually providing. So you get some recirculation happening through the hydraulic separator. From the secondary side, it's coming back out to the field without returning to the boiler. And this is similar, this is typical primary secondary system operation. And then the controls have to compensate to provide the additional hot water that's being requested from the secondary side. So this is where staging of the boilers will come into play. And thirdly, the flow in the secondary circuit is less than the primary because the boiler output exceeds the field load requirements. So the control valves in the field are starting to close down, The boiler hasn't compensated for that yet, so it's providing more water than is actually required in the secondary circuit. So in this case, a portion of the water in the primary circuit will recirculate through the separator and return directly to the boilers. This will increase the temperature of the return water in the primary circuit and may lead to boiler capacity reduction, which means the boilers, the controls in the boilers will reduce the heat input to the boiler to try and compensate for the reduced load in the field. So diagrammatically, there it is. Water from the boiler is recirculating back to the boiler because the field is not taking that water away. So this type of system is a more modern way of controlling the heating water system, and you don't need a bypass in this case necessarily. It depends on the complexity of the system, but with a hydraulic separator, such and similar to a chilled water decoupler, this is the bypass. Okay, but you need more pumps. So I think you'll find mostly these days when you're talking to or getting quotes for boilers, the boiler manufacturer will offer you a primary pump with the boiler, and also a hydraulic separator will be offered, so that you can put those in, and then the field side, they don't supply that. That's a separate supply, but the field side has to have the secondary pumps installed. Okay, now let's have a talk about boiler control and staging. This might be a little bit hard to get your head around, but once again, you can do a bit more research, and every project's going to be a bit different. So you need to talk to the people involved in the project, the suppliers of boilers, the controls people, and decide which way you're going to control the capacity of the system. There are various methods available to start and stop boilers. The boilers will be required to run only when the field is calling for heating. So if there's no call for heating out in the field, the boilers aren't running. If a zone temperature sensor in the field signals that heating is required, the corresponding air handling unit or fan coil unit heating water control valve will start to open. Okay, so you've got a temperature sensor in a space. It's saying that it needs heating. So the first thing that happens is the control valve starts to open at the coil. Typically, a boiler heating coil will be enabled when a control valve is more than 80% open for 5 minutes. Now, this is taken from the ERA design guide, DA28. It's one way of doing it. It's not the only way, but I've just given this as an example. So what it's saying is the valve has to be open 80% for 5 minutes before the control systems, the BMS DDC, actually sends a signal to the boiler that it wants it to start. Alternatively, a heating coil may be enabled when the average terminal heating control valve position is greater than 25%. That's a bit of a mouthful, but this applies to systems with terminal reheat, for example, VAV with heaters, hot water heaters, or small fan coil units. And what it's saying is the average of all the control valves position is greater than 25%. So that can be set up relatively easily in the BMS. The controls people just need to understand how you want to control it, and they can set that up. Now, these time delays ensure that the heating coil is sustained and prevents short cycling of the boiler. So you don't want to start a boiler as soon as the valve starts to open and then turn it off again, because it's going to meet the load very quickly if only one valve opens, and then the valve shuts and the boiler shuts off. So you don't want to be starting and stopping. That's the worst thing you can do with any machine. So you want to make sure that there is really a load out there, and then the boiler can start. Heating coils should be disabled typically around 18 degrees outdoor air temperature for systems without reheat or trim heat operation for dehumidification. Now this is in a situation where well, you don't have trim heating or reheating for dehumidification, obviously. In some cases, you will have, this is getting a little bit more complex systems now, but you might have cooling. You'll have a cooling coil and a heating coil, and or you might have zone heating coils for different terminal units, controlling dehumidification. So when you cool, when you put the air through the cooling coil, the humidity is reduced substantially. Some cases you need further dehumidification, and you might put the air through a heating coil to reduce the humidity even further. What I might do is put this on for a later discussion and talk about these systems, because it's getting into the more complex cycles of psychrometrics. For instance, labs, operating theatres, where you need to control humidity accurately, you may need heating for dehumidification. Lockouts based on outdoor air temperature are not possible if there is a non-seasonal process heating requirement such as domestic hot water. So you don't want to lock out the heating if you've got something that's relying on the heating source at all times. So if you've got a domestic hot water system attached to the heating water system through a heat exchanger or calorifier, you need to keep that online 24/7. So you can't have an outdoor air temperature lockout, because then you're going to lose your domestic hot water. Once again, minimisation of boiler heating coils is a fundamental factor in energy efficient operation. So you don't want to have, and as I said, it's detrimental to the boiler and other equipment if you're turning things on and off constantly. When a heating coil is confirmed by the control system, if the heating water pump is not already running, it will start in order to deliver heating water to the field. Boiler controls then receive a signal that the pump is running satisfactorily, or either a DP, differential pressure sensor in the pipework around the boiler, or the pump, or a flow switch in the hot water flow pipe. The boiler will then start and operate under its own controls and will maintain a preset leaving hot water temperature. So going back to this little sketch, when this differential pressure sensor, which is either across the boiler or the pump, senses that there's flow, the boiler controls receive a signal from the controls to say flow is confirmed and the boiler can start. Another option is a flow switch, but these are a bit unreliable and very not commonly used these days. They used to use them all the time for chillers, but it was just a paddle in the pipework, and if the paddle was pushed downstream and made contact, then the flow was established. But unfortunately, the paddles used to break and end up somewhere in the pipework, and the flow switches didn't work. So they don't get used much anymore and not recommended. Typically, the heating coil will be disabled when all air handling unit valves are less than 30% open for 5 minutes. Where the average terminal heating control valve position is less than 10%. The boiler will then shut down under its own control system safety devices. When all the control valves are closed, the hot water pump will stop. It shuts down. So have a think about that. It's not terribly difficult to understand, and the Aero Design Guide can give you a bit more information. Now just have a quick talk about boiler staging, similar again to chiller staging. If you've got multiple boilers, the the control system becomes a bit more complex, but usually follows the same parameters. And basically, you only want to have enough boilers running to meet the load. You don't want to run all boilers. If you only need one boiler, you only have one boiler. It's a little bit different with chillers. Sometimes you'll find with chillers, particularly magnetic bearing chillers, that it's actually more efficient to run 2 chillers at 50% load than to have one at 100% load. So just keep that in your head as well. When you're looking at chillers, there are other options to get the highest efficiency. So when you have multiple boilers, it's necessary to develop a staging strategy to optimize the boiler operation and efficiency. Again, referring to ERA DA28, the sample strategy could be. So boilers staging up. So this is when more boilers are required to meet the load. Primary hot water supply temperature is if the primary hot water supply temperature is more than 2 degrees below set point for more than 10 minutes. In other words, the current boiler can't meet the field load. So it's not able to achieve the design temperature. So if it's more than 2 degrees below the set point, let's say it's 80 degrees required, it can only get to 78 and it's flat out. So it's not able to meet the load. You need another boiler. Well, boiler staging down, which means you need less boilers to meet the load. If the return water temperature indicates that the current load is less than 85% of full load for the next stage down, based on comparison of the design and actual temperature change across the boiler, then you can turn a boiler off. You might want to have a read through that again, but all it's saying is that the control system is looking at what's happening in the field. It knows what the control valve positions are. It's looking at the temperatures in and out of the boiler and saying, well, actually, we don't need 2 boilers running or 3 boilers running. We can do it with less than that. And the boilers often come with their own control systems that look at all those things as well, look at all those parameters and decide how to control it. And it's all about energy efficiency, principally, and the best operating conditions for the boilers. Hot water temperature reset is another factor. It may be required or put in the system to reset the hot water supply temperature due to changes in the outside air temperature. So if the outside air temperature is going up, there's still a heating load in the building, but it's reducing because of the outside air temperature. You might want to reset the supply temperature. And so some considerations with doing that are, for non-condensing boilers, the limits within which the set point can be varied without risking boiler damage from condensation within the boiler may be limited. Okay, well, as was said earlier, at 54 degrees or lower, you get condensation in the boiler of the boiler flue vapor, which is acidic. And for a non-condensing boiler, that's a bad thing because it's going to cause corrosion in the flue and the boiler itself. It's not designed for that. So it's designed to be above 54 and typically around 60 degrees is the return for a non-condensing boiler. Considerably more scope is available with a condensing boiler, which is designed to recover heat from the flue gas, as we've said, by condensing the vapor. There's a comment here. Hot water resets work well for radiator systems, but can cause rapid degradation of capacity for fan coils and air handlers. What that means is if you're reducing the hot water supply temperature, the capacity of the coils is going to reduce as well. The coils have been designed for a given inlet and outlet temperature, let's say designed for 80 degrees in, 60 degrees out. If you reduce the inlet temperature, the performance of that heat exchanger or coil is going to change. So just be careful of that. You might want to have a look at that closely to make sure that it's going to work okay. So just a summary of the common issues. Excessive reset may cause condensation damage in non-condensing boilers and flues. Excessive reset may cause system capacity to fail to meet system demand. And finally, return water staging set points must be defined so that they track with the variable hot water temperature set point. Again, that's a bit of a mouthful. What it's saying is, if you're going to reset the supply temperature, then you need to be resetting the return temperature as well to try and make sure that you're not causing condensation issues. Just need to think about the detrimental things that can occur if you're going to reset the supply temperature. Well, that's the end of the notes. We've got a few minutes if there's any questions.
Yeah, I've got a quick question about the bypass pressure drop. So is the reason behind trying to make sure that pressure drop is equivalent or thereabouts to the field, is that to do with sort of valve authority?
Not really. No, it's about making sure that the control valve can handle the full flow of the water. I mean, yes and no authority, but
I suppose better question is, what's the flip side? If it wasn't sized to have enough pressure drop, what would then happen? Would you not be able to bypass enough water, or would you just not be able to control it well enough?
you wouldn't be able to control it well enough if the pressure drop is too low.
It would just like modulate completely. Slight modulations would have large differences in the flow.
It's probably going to go up and down. It's going to try and close and open and close and open, and which is called hunting.
Yeah.
And you want to avoid hunting of valves in particular. And that's, I think I mentioned, to maintain the system stability.
Yeah.
So let's say the pump delivers 10 litres a second at 200 kPa, which normally goes out to the field. When the field is fully open, all that water is going out to the field, and it's all stable. Everything's fine. When the valves start to close, and the bypass starts to open, it's got to have a fairly high pressure drop so that it's not robbing water from the field initially. So the water can still get out to the field, and the pressure drop through the bypass valve will be very high, but when it gets fully open, the pressure drop should be the same as the field, so that the pump sees the same. The pump doesn't know that there's any difference. It still thinks it's pumping out to the field because it's going through the bypass. So the pressure drop needs to be the same for that reason. But obviously it's going to be in between most of the time. So there is valve authority there that you want to restrict the flow through the bypass at part load. Part load is always going to be the critical situation. But the pressure drop will equal the field pressure drop when the valve is fully open.
Yeah.
But at that point, if you've got full flow through the bypass, then you don't need the heating system anymore. And that's a trigger to start shutting down the boiler. Does that make sense?
Yeah, yeah.
Anything else? No? Okay, well, next week, we're going to talk about cooling towers. We talked about chillers, air-cooled and water-cooled. Now we're going to talk about, next week, we'll talk about cooling towers and fluid coolers, which are the heat rejection part of a water-cooled chilled water system. Very interesting. A lot of things to learn about cooling towers, and in 1 hour, we're not going to cover it all, but hopefully we'll be able to give you enough information to tickle your curiosity, let's say, and learn a few things that you need to be aware of when you're looking at cooling towers. Cooling towers apply mainly to larger projects, and you know, a lot of the work you're doing at the moment may be just air-cooled DX type systems, but you will get involved in larger chill water systems with cooling towers, and I think it's a very interesting topic. I hope that you'll get something out of that. So I'll issue the notes on Thursday as usual, and see you same time next Tuesday, if there's no other questions.
Thank you.
Thanks, Ben.
No?
Thank you.
Okay.
Thanks, Peter.
Thanks, guys.
Thank you.
Thanks.
See you next